So going over questions from last day, someone asked for 5B. Okay. In a group of students, the probability that a student chosen at random walks to school is 0.35. You know what? I'm going to write that as follows. The probability of W is 0.35. Is that okay, Silka? I've written something down. The probability that a student has blonde hair is 0.2. Okay. If the, I think there might be a typo in this. I stole this from a different book, and I think now I'm looking, and I think instead of brown, I think this is meant to be blonde. I think we're finding and, but let me double check and confirm that, okay? Oh, it says if the probability that we walk or have blonde hair, so I know the probability of walk or blonde is 0.45. And I think what it wants us to find is and, the overlap. Is that okay? Now here's what we said last day. This was our probability formula. Those of you that were away last day, I also need to give you a formula sheet. I forgot to give you one. I'll give you one in a second. The probability of W or B, we said that or means add them together minus the overlap. Is that okay? Now, what are they asking me to find? I think they're asking me to find that. That must mean they've given me all the other numbers, I hope. Did they tell me or? What? I have no idea what you said. Okay, so it's going to be 0.45 equals, did they tell me walking? Yeah? 0.35 plus, did they tell me blonde? 0.2 minus, and this is what I'm trying to find. I guess it's going to be 0.45 equals, I can add this in my head, 0.55 minus and. Oh. Sorry? I did. 0.35 plus 0.2 is 0.55. Is it not? Right? That just dropped down, isn't it? We're doing equation solving, right, Foster? Right? Yeah. So I just dropped that down, and I said, hey, those are like terms, minus, and this is what I want right here. Yeah. My argument is, I think, 0.1, I think. With me or no? We have to solve it, right? And so you would go like this. You would go minus 0.55 from both sides. And you would have negative 0.1 equals negative and. I'm not writing the whole thing out because I'm running out of room. And then divide by negative 1, divide by negative 1. You get and is 0.1. Is that okay? I think the probability of walking and I think it's blonde, not brown, is 0.1. Is that what it says in the back? I think. Okay? So what I'm saying is, if you all look up for a second, in this formula there are 1, 2, 3, 4 things. I can give you any 3 and expect you to find the 4th with like equation solving. Is that all right? That'll be fair game as far as I'm concerned. Any other questions from the homework? Going once. Please be honest, I'm not writing down names. I just want to know, this is going to help me pace my lesson. How many of you have finished the homework from last day? How many of you not finished the homework from last day? Okay, so you're going to have to kind of, you know what, we'll see. We'll play it by ear, but you want to keep up with this stuff. Don't slack off. Christmas is not till Friday. So I think we'll get about halfway through the lesson today. I'll give you time to work on the homework. I'll finish off the lesson Wednesday. We'll go over the combinatorics test Wednesday, and you'll get time to work on the homework Wednesday. Okay? And I think it was Justin I picked on last time. I think I'll pick on Justin again. Justin, can you read me the title? It says Lesson 4, what?
The event A and B.
So last day we talked about or. What if you wanted to find the probability of one thing or the other happening? Today we're going to say, what if you want the probability of and? What if you want to find out what are the odds of them both happening? Either at the same time, or if it's separate events, one after the other. So, for example, what's the probability of, suppose Foster's flipping a coin and you're rolling a die, what's the probability of Foster getting a head and you getting a 5? Okay? And much like last time, I can summarize this whole lesson in one word. And means multiply. With some qualifications and weird exceptions. But or, when I see the word or, I think, you know what? I'm probably going to add the numbers together. So, for example, suppose Foster's flipping ahead. What's the probability of Foster getting ahead? Come on, folks. What's the probability of Foster getting ahead? 1 out of 2. Flipping a coin? Yes. What's the probability of you rolling a 5? What's the probability of Foster getting ahead or you rolling a 5? Whatever 1/2 plus 1/6 is. And you could use the fraction button on your calculator or whatever. What's the probability of Foster getting ahead and you rolling a 5? Whatever 1/2 times 1/6 is, which is, I think, 1/12. That's the whole lesson, sort of, in a nutshell. But let's walk through this. So I wrote down for the objectives, hey, when do you multiply probabilities? And the short answer, Kyla, is when you see the word and. Situation 1. We're going to have to, though, give you some notation. And Rosanna, we're going to have to introduce a concept called conditional probability, or in English, it depends on what happened before probability, and you'll see why in a second. So situation number 1 says, drawing 2 balls from this pot without replacement. We've got marbles, okay? We've got 2 white marbles and 1 black marble. So suppose I select a, oh, I got the screen frozen still, Mr. Dueck, duh. Am I live, though? I am, okay. Suppose I draw a marble, and I'm going to define 2 events. The first event, A, is the first ball is white. The second event, A, is the second ball, B is the second ball is white. What's the probability of A? Well, first of all, what we're going to do is we're going to do a tree. So I've drawn out the tree for you already. I've said, okay, oh, my OneNote's freezing here. There we go. Still going to work. There we go. To solve these questions, especially when there's 2 events, I find a probability tree is my best tool. And here's what I mean. What we're going to do is we're going to sketch out a blank tree. So this says first ball white, not white. Second ball white, not white. Second ball white, not white. Here would be if the first ball was not white. Here would be if the first ball was white. And we're going to use what's called a weighted probability tree. And by that I mean we're going to write the probabilities, Rachel, on the branches. So Rachel, my angel, we have this bucket, this jar, this pot right here. What's the probability right now that I get a white ball? So what I'd like you all to do is write that on this branch right here. This is event A. We're going to say that branch is 2 out of 3. What's the probability of getting a black or getting not white? Let's fill that in over here. This is going to be probably the most useful tool I teach you all unit. This is my fallback. Now, Rachel, if we walk down this branch, we already picked a white ball, and we're not replacing them. So, if you already got a white ball, what are the odds that the second ball is white? How many white balls are there left in the bucket, in the pot? Out of? So 1 out of what? 2. Event B would be that, because you've got 1 white out of 2 left. What are the odds of getting a black on that second draw? Let's go back to the top of the tree. We're going to go down the other branch. Now, the other branch, you didn't get a white ball. In fact, you got a black ball. So what's the odds of getting a white ball on the second draw here? How many are left in the bucket? Out of how many total? It's going to be 2 out of 2 and none out of 2. some nice things about a tree. There's some built-in error checks. Don't write this down, just watch. Oh, got my latecomer. Look up, this is really handy. Some built-in error checks, and this will always work. Do you notice that these branches here add to 1, 2/3 plus 1/3? Do you notice that that branch there adds to 1? And do you notice that that branch there adds to 1? It's either 2/3 plus 1/3, 3/3, 1/2 plus 1/2, 2/2, 2/2 plus no halves. That will always work. If you're doing your tree right, any level, any fork, they should all add to 1, because that means, oh, that means you've covered every outcome. Because we did say if you cover every possibility, what does it have to add to? 1. We said the probability of something happening or not happening. Okay? So here's our tree. So it says, find over here, find the probability of A. You already said that, Rachel, was 2 out of 3. See it on my tree? Find, and then I wrote down here, what's the probability of B given that the first ball drawn is white? What they're saying is, all right, suppose you know you're on this branch, not this branch. What's the probability of that? Now, the only problem is that's way too much writing. Here is the abbreviation. We write this. The probability of B, the abbreviation for given that is a vertical line. A occurred. We would write it that way. The probability of B, given that you're down the branch that A occurred, is what? You see it? Rosanna, you see it? Given that you're down branch A, what's the probability of B? Nice and loud. I can't hear you. Yeah, 1/2. Yes, I heard you. I'm trying to get everybody else participating here. Got that back row and wake up. Okay? What's the probability of A and B? Now, in English, what does it mean? What's the probability of 2 whites in a row? Right? Because event A was the first ball is white. Event B is the second ball is white. What are the odds of getting 2 whites in a row? The answer is 2 out of 3 times 1 out of 2. Now, multiplying fractions is the easiest operation of all. It's top times top, bottom times bottom. 2 out of 6. And I know that's 1/3, but I told you last day, I will only reduce fractions at the very end if I want to match the answer in the back of the book. Otherwise, I'll leave it like that. Okay? And then it says events A and B are dependent because I'm going to leave that blank for a second. We're going to talk about, so last day we looked at what was called mutually exclusive. That meant no overlap, couldn't both happen at the same time. Today we're going to be talking about a new word, dependence. Talk about how that works in a second. Situation 2. What's the difference between situation 1 and situation 2, Cole? Read very carefully. There's one key word. Okay, in situation 2, after you pick a ball, you're putting it back in the pot. And we're going to define the same 2 events. The first ball is white, event A, event B, the second ball is white. And we're going to do a tree again. So we have A, not A, B, not B, B, not B. Cole, my friend, reaching in, what are the odds that the first ball is white? How many whites are there? Out of? What's the odds that the first ball is not white? Okay. Now, you put the ball back, shake things up. What are the odds that the second ball is white? How many whites are left in the pot? 2 out of? What are the odds that we're not white? 1 out of 3. Now, down the other branch, you got a black ball. But you put it back in, because it says with replacement. You shook it up. What are the odds that the second ball is white? And? First of all, double check. Does each fork add to 1? So I didn't screw up. That's, again, a quick way to double check to make sure you haven't made a sloppy mistake. Okay? Each fork adds to 1. Do you notice, though, that this branch is identical to this branch? That if it happened or didn't happen, didn't affect the odds later on. Compared to Christina here, whether it happened or not, that changed the odds of your second event happening. See it? Okay. Events A and B are independent because the easy way is the two bottom forks are identical. That's how I can tell from a tree. I know two events are independent because the odds of the first one happening didn't change, the event of the first one occurring did not change whether or not the second one occurred. Up here, events A and B are dependent because the two bottom forks are not identical. That's not the math definition. That's the Mr. Dueck's handy dandy when I'm doing a tree, I can glance at it and figure it out very quickly definition. Okay? We're going to do a mathematical definition, Rosanna, in just a second. But there's my, hey, if I notice that event A doesn't change event B's odds, they're independent. If I notice that event A does change event B's odds, they're dependent because it depends on whether A happened or not. You good, Kayvon? Hey, let's fill in, Kayvon, let's fill in these questions here. So it said, find probability of A. The probability that the first ball is white, what did we say? What are the odds that the first ball is white? 2/3. What are the odds of event B given that the first ball drawn is white? First of all, we write it like this. Probability of B given A. What's the probability of event B given that A has occurred? Yeah, and again, Kayvon, what this is saying is, okay, that given A says walk down here. Use that number. What's the probability of A and B? It's going to be 2/3 times 2/3, which is what? Brooke, you with me so far okay? Yeah? Scroll back up, please. And next to where we wrote the probability of B given A, we're going to add another one. I'll do it in red. What's the probability of B given not A? Suppose I told you that A did not occur, which means go down the right-hand branch, Christine, yes? What's the probability of B? Caitlin? Scroll down here. We're going to do the same question. What's the probability of B given not A? You're right. What's the probability of B if you're on this branch, given the not A branch? 2/3. Look up once you've written that down. Roy, do you notice that the odds of B occurring are identical whether or not A occurred? Do you notice that the odds of B occurring are not identical? It depends on whether A occurred or didn't occur. That changes the odds. That's the mathematical definition of independence. So where it says events A and B are dependent because probability of B given A is not the same as the probability of B given not A. That's the mathematical definition, Seb. It says, you know what? The odds change depending on which branch you go down. Whether or not A occurs, that changes the odds of whether or not B occurs. And I'll give you some real-life examples in a second, but I'm doing the mathematical definition right now. Oh, and you know what? They're independent here because the probability of B given A is identical to the probability of B given A, not A, Mr. Dueck. Doesn't matter which branch you went down, the second level was identical. Let me give you an example of two events that are independent. Rolling 2 dice. Incoming. Incoming. Does what Jake rolls have any effect on what Foster rolls? No, they're independent. So if I said, what's the probability of Foster rolling a 3 and Jake rolling a 4? What's the probability of Foster rolling a 3? 1 out of 6. What's the probability of Jake rolling a 4? It's 1 out of 6 times 1 out of 6, 1 out of 36. Oh, and it doesn't matter whether Jake rolls a 5 or not. It doesn't change his. Okay? What is dependent? Picking cards. Put the die down. Pick a card. Don't look at it. Jake, pick a card. Don't look at it. What's the probability that with the second card, Jake drew an ace? Depends. What does it depend on? See, if Foster has an ace, how many aces were left for Jake to pick from? Only 3. But if Foster doesn't have an ace, how many aces are left for Jake to pick from? 4. If you drew a branch tree, the branches would be different. Branches would be different. It depends. Did you get an ace? Did you get an ace? No. Okay. Cards are great. Cards without replacement are great examples of it depends. What cards are left depend on what cards have already been picked. Dice, coins, independent. If you flip 10 heads in a row, that doesn't change the probability of getting an 11th head. It's still 1/2, 1/2. Or the odds are still 50-50, 1-1. The multiplication law says this. If you want to find A and B, it's the probability of A times the probability of B, but make sure you go down branch A, given that A has occurred. Key idea here, Colin, is what does and mean? Multiply. But multiply down the correct branch. By the way, if I wanted to, I could get the probability of B given A by itself by dividing. The probability of A is multiplying. I could move it over. This formula here, this will become important later on. So don't freak out about it yet. We're going to do like 3 days or 2 days on it. The special subcase. A and B are independent if the probability of B given A is the same as the probability of B down any branch. It's what I wrote here, except I said B given A and B given not A are identical. What we're really saying is it doesn't matter which branch you go down. Well, then it looks like that. Here's what I'm saying. Here's the key idea. Emma, in both of these, what does and mean? Multiply. Okay? So I don't change my approach whether they're dependent or independent. However, I look at my tree afterwards and I can say, oh, the bottom levels are identical, independent. It matters which branch I go down, instead of matters, it depends which branch I go down, they're dependent. It's easier if I do some examples. Example 1. 2 cards are drawn without replacement from a shuffled deck of 52 cards. All of you underline the phrase without replacement. This is going to be a dependent probability event because we're not replacing the cards. We're going to define the following events. Event A, the first card is a face card. Event B, the second card is a face card. Okay. How many cards are we picking? How many cards are we picking? How many cards are we picking? 2. This is a job for a tree. Eventually, when we're picking 5 or 6 cards, we'll stop using a tree because it's going to be, you couldn't fit it on one page. But 2 events, 2 things, I almost always fall back on a tree. So it's going to look like this. My tree is going to say A or not A. And let's fill in the branches. How many face cards what is a face card? Jack, Queen, or King? So there's 3 face cards per suit. How many suits are there? 4. Using the fundamental counting principle, how many face cards are there then in the deck? 12. 4 suits, 3 cards, multiple. Okay. 12 out of 52. How many non-face cards are there in the deck? 40 out of. Double check, does that add to 1? Yes. Now, down the right-hand branch, we picked a face card. Sorry, down the left-hand branch. I'm reversing everything for you guys, sorry. Down the left-hand branch, we picked a face card. So it's going to be, let's change colors, Mr. Dueck. Let's go with black. B, not B, B, not B. Down the left-hand branch, we picked a face card, event A. How many face cards are left in the deck now? 11 out of 51. How many non-face cards are left in the deck? 40 out of 51. Double check, does that add to 1? Yeah, there's our built-in error check. Let's fill in the other branch. Now, in the other branch, Jordan, we didn't get a face card. So, Jordan, how many face cards are still left in the deck then?
12.
Out of?
51.
How many non-face cards are left in the deck? 39 out of? Jordan, are the 2 bottom branches identical? That's how you know these are dependent. It also means that the probability of B given A isn't the same as the probability of B given not A. 11 out of 51 isn't the same as 12 out of 51, but that's how you know. Okay, we've got our tree. What does A want? Probability of A and B. You know what? That is going to be that branch there. Right? What does and mean? It's going to be 12 out of 52 and 11 out of 51. What's 12 times 11 over what's 26 times, sorry, what's 52 times 51? 12 times 11 is 132, and I think 52 times 51 is 2652. Double check me. Yeah. How do you multiply fractions, Colin? That's the easiest. Top times top, bottom times bottom. And I'm sure that reduces, but I don't care. B. B. Kyla, can you read B to me, please? Probability of what? Read B to me, please. Look up. Yeah, this. And just read what's there. So what does that bar mean? So not A and? Okay, that's what we wrote. Now let's translate it into English. What does not A mean? The first card is what? Not a face card. And the second card? Okay. You know what? I think that's first card not, second, I think it's that branch, isn't it? Yes? I don't want to mess up my tree, but that's what we're talking about. Multiply down. And means multiply. So it's going to be 40 out of 52 and 12 out of 51. Which is what? 480 over 2652. We're going to add a part C before you turn the page. What's the probability of B? In English, what does that mean? What's the probability that what? Rosanna, you're right, loud. Okay. I think that means this. I think that means this branch or this branch. What does or mean? So it's going to be multiply 12 out of 52 and 11 out of 51. That's the first branch. Or 40 out of 52 and 12 out of 51. Let me see if I can get all this. I can't quite get all this onto one page. Do you see what we're saying now? You want the really short rule for a tree? It's multiply down, add across. If you really want to simplify probability into one sentence, except there's exceptions. But if you give me a tree and you start asking me questions about it, Brooke, as long as I can translate the symbols into the appropriate branch, and that's a tricky thing, we're going to practice that, it's multiply down and add across or. Which is what, by the way, here? Oh, you know what? It's going to be 132 over 2652 or 480 over 2652. How do I add fractions? What do I need to add fractions? A common denominator. Oh, have I got a common denominator? So it's going to be over 2652. What is 132 plus 480? Kayvon, sorry? 612? Anybody else? Is that right? Okay. Hey, you got your calculator? Reduce that to lowest terms now. I just want to know. Give it to me either as a fraction or as a decimal. What'd you get? 3 over 13? What is that as a decimal? What is 3 divided by 13? 0.23, so almost 1 in 4 odds, but not quite, because 0.25 be 1 in 4 odds. Let's find out. Pick a card. Lay it down. Pick the second card. This is the probability that the second card is a face card is 1 in 4, roughly. Hey! He beat the odds. He beat the probability. You got to hold it up so they can see. Nobody saw. Just the queen. Just the queen. Okay, the second card was a face card. I'll bet you if we did it again, probably it wouldn't happen again. Might. Probably not. Okay? Now turn the page. Do you know what words I would underline in example 2? I probably would. Read A, B, and C. What events are we talking about here? What's the common event we're mentioning here? What's the common event? Hearts. So you know what? What would be a good letter to use for hearts? Here's my tree. I'm going to go like this. H1, that'll be a heart on the first card. Not H1, that'll be you didn't get a heart on the first card. What would be a good way to write a heart on the second card? H what? H2? Not H2. H2. Not H2. Brooke, what we're saying here is, look, when you pick the first card, it's either a heart or it isn't. When you pick the second card, it's a heart or it isn't. It's a heart or it isn't. Let's fill in the branches, the probabilities. How many hearts are there in the deck? 13 out of? Let's fill in the first level then. So the first level is going to be 13 out of 52. Hey, how many non-hearts are there in the deck then? Colin. 39 out of? Double check, that adds to 1. Yay! Move down a branch. Now, let's do the left-hand branch. In the left-hand branch, you got a heart. How many hearts are now left in the deck? 12 out of? Oh, 51, Mr. Dueck. How many non-hearts are left in the deck if you picked a heart the first time? or given that you picked a heart the first time. 39 out of 51. Down the right-hand branch, we didn't get a heart. How many hearts are left in the deck? 13 out of 51. How many non-hearts are left in the deck? 38 out of 51. Sean, my friend, are these two branches identical to those two branches? Are the two bottom forks identical? Say no. You know what I mean? Are the fractions identical? No. You know what? That means this is dependent. If they were identical, then I would say these are independent events. But dependent. Have we got our tree set up, Christina? Nod. Then we can start answering the questions. Brooke, what's the first thing it wants me to do? Find the probability what? Which branch is that? H1, H2. Yeah, you know what? Let's write that, actually, because that can be our notation. So what it's asking us to find is the probability of H1, comma, H2. And I use a comma, just like in English, a comma replaces the word and. Right? Why not? What am I going to do, Brooke, with this number here and this number here? What am I going to do with the 13 out of 52 and the 12 out of 51? Because you want the first heart and the second heart. Yes? 13 out of 52 and 12 out of 51. I know that 52 times 51, I've done this one so often, it's 2652. What's 13 times 12? It's going to be 144 plus 12. It's going to be 156. Is that what you said? Which I'm sure reduces, but I don't care. Connor, what's B asking me to find?
Neither card is a heart.
Which two events is that? Kayvon, what? Not H1 followed by? You know what? It's the far right-hand branch. Yes? In our notation, we would write it like this. H1 not, comma, H2 not. Kayvon, what times what? It's going to be over 2652. I have no idea what 39 times 38 is. Sorry? 1482. Foster, we're good? Because your attention span was somewhere. Roy, can you read C to me?
Exactly one of the two cards is a heart.
Ah, one but not both. Okay. I'm going to use, I think that's more than one branch, isn't it? So I'm going to use the check mark method. I'm going to put a check mark underneath the appropriate branches. So you guys can tell me, would I put a check mark underneath the first branch, the left-hand branch? Why not? Oh, that's two hearts, and it says exactly one. So I'm going to say, no, no. Would I put a check mark under here? Yeah? Would I put a check mark under the third branch? Yeah? Would I put a check mark under the fourth branch? Okay. So, if you wanted to write it in notation, Sean, here's what we're really saying. This is the probability that the first one is a heart and the second isn't, or the probability that the first one isn't a heart and the second is. Right?
Yeah.
What does or mean? I'm building an equation here, building an expression here. What's the comma an abbreviation for? And? And what does and mean? oh, you know what? It's going to be that times that, or that times that. It's going to be 13 out of 52 and 39 out of 51, or 39 out of 52 and 13 out of 51. It's going to be out of 2652 because both of them end up with 20. Well, you know what? I went too fast. I lost a few of you. Let me slow down. The first fraction is out of 2652 because that's what 52 times 51 is. Cole, two-card questions without replacement, it's always going to be 52 times 51 on the bottom. And so after a while, you just start to notice that's the number. Hey, what's 13 times, that's a 9, Mr. Dueck. What's 13 times 39? 507? Yeah? What? I heard someone make a little leap there. Was that Rosanna? You were right. What? What did you say? As it turns out in this one, each fraction ends up being identical, even though the numbers came from different spots. I did notice that each fraction is identical. So you know what? I agree with you. As a shortcut, I'm just going to go. So the bottom is still going to be 2652, but the top is going to be 1014, 507 times 2. That won't always happen, but that'll happen fairly often if you're going all the way to the bottom of a tree and you're taking branches that are opposites of each other. And these were two branches that were opposites of each other. It was yes, no, and then no, yes. I can't say that's a rule or anything, Roy, but if you spot it, Rosanna, sure, feel free. Good shortcut. Last one. We're going to pause here. D. What's D asking us to do? Silka, can you read D to me, please? Ace, you know what? I got to do a new tree. I got to do a new tree. Okay? Hang on. Maybe, because it's the same event twice in a row, ace, ace, maybe I can imagine the tree in my head. We're going to try. Show you what I mean. I think what it's asking for is this. Yes? Is that okay? Yeah. By the way, we're talking about a branch like this. Aren't we? Ace 1, ace 2. And the only time I do this, Christina, as a shortcut is if it's the same event over and over and over, like both aces, or if they said 3 aces in a row or 4 aces in a row, I can usually visualize one branch because, Silka, how many aces are there in the deck right now? No, how many aces are there in the, oh, I want to gamble with you. How many aces are there in the deck right now, folks? 4 out of? I think the first number would be 4 out of 52, and you pick an ace. How many aces are left in the deck? 3 out of? I think this, because, Caitlin, it's the same event twice in a row, you may find you can get away without doing a tree or even just doing the one branch and kind of saying, I got my template, because it would be 4 out of 52, 3 out of 51. I find if it's the same thing, Rachel, over and over, I can keep track of that. If they had said an ace followed by a king, okay, that I'd have to do a tree for because I'd be using multiple branches and things like that. 12.